Jai Hind everyone. I am Vivek Kumar Pansari, Assistant Professor in Department of Mechanical Engineering at Ajay Kumar Garg Engineering College, Ghaziabad. Today in this video, I would like to continue the topic of strength of materials, and in my previous video related to strength of materials, I had introduced the topic as well as the basic concepts related to stress, strain, elastic behavior of material. So, these three things I tried to cover in my earlier video. In this video, I would like to continue with the same topic of elastic behavior first, then some application of this particular concept, means the Hooke's law. So, first of all, when we go for the relation of the stress and strain, then stress and strain both terms are related by the Hooke's law. And what this law states? This law states that within the elastic limit, meaning of this, whenever a material is stressed, it is stressed up to that level that after removal of deforming force, material is regaining its actual shape and size. This is what the meaning of elastic limit. So, within the elastic limit, stress is directly proportional to strain. That stress may be normal stress, shear stress. That strain may be longitudinal strain, volumetric strain, or the shear strain. So, whenever we are talking about the deformation of any body, that body is stressed, and within the elastic range, the stress is directly proportional to strain. And whenever we are removing the proportionality sign, then it will be replaced by a constant. That constant is known as elastic constant. Okay. So, elastic constant. So, different elastic constants we will be discussing here in this particular video. So, first of all, it must be clear what is the Hooke's law. So, again I am repeating the statement: within the elastic limit of any body, stress is directly proportional to strain. Okay. So, by this Hooke's law, we can define different elastic constant or modulus of elasticity. Okay. So, Young's modulus of elasticity. First, it is the Young's modulus of elasticity. Second is the bulk modulus of elasticity. Third is the modulus of rigidity. There are three different modulus of elasticity or elastic constant we deal. Whenever we are dealing with the longitudinal strain, when we are dealing with the change in length means, if I am talking about the change in length, the material is subjected to normal stresses. So, if I am talking about this particular condition, then the Young's modulus of elasticity will come in picture. What is here? What I can say, if sigma represents the normal stress, okay, then E is modulus of elasticity, then here it will be longitudinal strain, epsilon L. So, the modulus of elasticity here, E, will be the ratio of sigma upon epsilon L. Okay. So, this is what the modulus of elasticity. Okay. This is coming from the Hooke's law. Stress sigma is directly proportional to strain. It may be any kind of a strain, but whenever I am talking about the change in length, it must be longitudinal strain. When I am removing the proportionality sign, a elastic constant comes in picture, which is known as modulus of elasticity or Young's modulus. So, this is what the E. Okay. Now, whenever I am talking about the volumetric change, so in previous video also, whenever a block is subjected to like and equal stresses on all its faces, okay, on all the 6 faces, it is having a normal stress, then there will be the change in volume, and that volume change will be taken with respect to actual volume, then it is a volumetric strain. So, whenever I am talking about the change in volume and normal stress, then elastic constant will be bulk modulus. Bulk means bulk is related to volume. So, that is why it is the ratio of normal stress and volumetric strain. Whenever we are dealing with tangential force, whenever we are dealing with tangential force or tangential stress. In that condition, what we are observing? We are observing the change in shape, okay. So, change in shape, it is given by phi or theta. So, here the stress will be shearing stress, the strain will be shearing strain. So, modulus of rigidity, rigidity is related to shape change, rigidity is the term related to shape change, okay. So, resistance against the change of shape. So, whenever we are dealing with shearing stress and shearing strain, then the modulus named as modulus of rigidity. So, we must keep this thing in mind that there are three different elastic constants we generally deal. If we are dealing with normal stress and longitudinal strain, then it is known as modulus of elasticity or Young's modulus. Whenever we are dealing with normal stress and volumetric strain, then it is termed as bulk modulus. Whenever we are dealing with shearing stress and shearing strain, that modulus of elasticity or elastic constant is known as modulus of rigidity. Okay. So, these are the three different elastic constants. Now, one more thing related to this Poisson's ratio. What we generally observe, if I say I have applied some force, because of that force it is elongated, neither we are adding any material nor we are removing, it means the volume will remain same. So, if the volume remains same and length is increasing, it means obviously any other dimensions are decreasing. So, we can say within the elastic limit, the longitudinal strain is always accompanied by a lateral strain. It is not necessary that length will always increase, length may decrease also. So, other dimensions will increase. So, Poisson's ratio is the relation between longitudinal and lateral strain, it is the ratio. So, this is what shown here also. Okay. So, this cylinder is subjected to what? It is subjected to tensile forces here. Because of these tensile forces, its length is increased. So, cross section we are observing is decreased. Here in another, when the cylinder is compressed, then its cross section is increased. So, Poisson's ratio relates these things. So, it is the ratio within the elastic limit, the ratio of lateral strain means in the perpendicular direction of force. So, it is the ratio of lateral strain to longitudinal strain, and within the elastic limit for a particular material, it is a constant quantity. So, this is what known as Poisson's ratio. Okay. This is written also here, when a body is subjected to axial tensile force, it elongates and contracts laterally. Okay. Similarly, it will contract and its sides expand laterally when subjected to compressive, and the ratio of these two type of strains are known as Poisson's ratio. Negative sign comes in picture, okay, here. So, Poisson's ratio generally indicated by nu. Okay, it is the ratio of lateral strain to longitudinal strain, and within the elastic limit for a particular material, this is a constant quantity. Negative sign indicates what? If length is increasing, if positive strain in longitudinal direction, then obviously in lateral dimension there will be negative strain. So, that is why the negative sign is indicated. And its value Poisson's ratio, it is a dimensionless quantity and its value varies from 0 to 0.5. Okay. So, this is what the Poisson's ratio, another important concept here. So, for different materials like steel, cast iron, concrete, we can say the Poisson's ratio, it is in between 0.25 to 0.33 for steel. For cast iron, it is 0.23 to 0.27. For concrete, it is around 0.2. For cork, which we generally place over the water bottles, okay, it is nearly 0. So, these are the some values of Poisson's ratio for different materials. Okay. Now, one more interesting thing, now we can apply the concept of Hooke's law. Basically, it is based on Hooke's law simply, nothing else. What we did? We, according to Hooke's law, we have written that sigma equals to E into epsilon L. Sigma is the normal stress here, and epsilon L is longitudinal strain. Okay. I can write this sigma I can write this sigma as P upon A, and it is E epsilon L delta L upon L. Okay, it is delta L upon L. So delta L upon L, whenever it is coming out delta L upon L. So from this, if I have to find out delta L or delta, okay, so it is coming out PL upon AE. So this is what the change in length. So whenever a bar is subjected to axial tensile load, then the change in length will be given by this particular relation. Nothing very special. It is P upon A. It is indicating stress. Delta upon L or delta L upon L indicates what? Delta L upon L indicates what? It is indicating the longitudinal strain, and E is the modulus of elasticity. So this is what for finding out change in length. Okay, now we can go for one simple form numerical also. A mild steel wire of 5 mm in dia and 1 meter long. If the wire is subjected to an axial tensile load of 10 kilonewton, so the load is given 10 kilonewton, the diameter is given 5 mm, the length is given, L is given. Okay, so L, capital L is available, A is available in terms of pi by 4 d square, the P is available 10 kilonewton, E it is 200 gigapascal, so I can write 200 into 10 to the power 9. Okay, so all the things are available to us, P, L, A, E. By putting all these, we can calculate the change in length, the elongation in the bar. Now, if the bar is not prismatic, if the bar is something like tapered, its diameter is changing from D1 to D2, then in this particular type of problem, when the diameter is not uniform, then also we can find out the change in length delta. It will be 4 PL upon pi E D1 D2. So for remembering this, there is a very good way of remembering it. So earlier what we did, delta equals to L upon A E. Okay, PL upon A. What we can write? PL, we can write this pi by 4 d square upon E. It is for uniform prismatic bar. Okay, uniform diameter prismatic bar, but here the bar is tapered, so it is changing from D1 to D2. So this d square can be written as D1 D2 here. So this is the way we can keep this formula in mind. The elongation of tapered bar because of a tensile axial load, the extension will be 4 PL upon pi E D1 D2. How to find out? How to find out this? How it is done? So at x distance, we have considered a disc of uniform diameter dx. So this dx, this is subjected to load P. Okay, this disc is subjected to load P. Okay, now consider the deformation of this, extension of this. What we can write? P L, in place of L, the length of this dx. A, in place of A, we can write pi by 4. What we can write? Dx square, diameter at x distance, into E. This is what the extension of this circular disc of dx thickness, which is at x distance. If I integrate this from 0 to L, then the result is coming out 4 PL upon pi E D1 D2. So this is the way. So if you want to derive this, then by this way you can derive this, or if you want to remember this, then the relation, or how to remember, this is already told to you, how to remember this. Okay. Then elongation of body due to its self weight. Elongation of body due to its self weight. So okay, now consider a body, consider a bar of length L, okay, of length L. Okay, this is what the bar is. Okay, I am considering a small section of dx thickness at x distance. The cross section of this is A. Cross section of this is A. So, elongation, just consider the elongation of this dx element. Okay. So, this dx element I have taken out. It is subjected to load. The load will be, if small w is the weight per unit volume. So, I can write W A x, the weight below the dx element. So, obviously, on the other side also it will be W A x. So, elongation of this will be, I can write in terms of P L upon A. So, P, in place of P I can write W A x, in place of L I can write dx, A the area, E is this. Integrate this from 0 to L, so it is W A x. So, A and A are getting cancelled. Okay. It is coming out what? W x square upon 2 E, W x square upon 2 E. So, whenever I am putting this x as a within the limit of 0 to L, so it will be coming out W L square upon 2 E, or whenever this W is what? W is the weight per unit volume, W is weight per unit volume. So, W L square upon 2 E. Now, the relation is delta equal to small w L square upon 2 E. Now, W L square upon 2 E, multiply it with A, divide it with A. So, this becomes what? This becomes W A L, small w into A into L. This is the total weight of the bar. So, what can I write now? Delta. I can write it W L upon 2 A E. So, two relations we can keep in mind. One is in terms of weight per unit volume, which is W L square upon 2 E. Another one, capital W L upon 2 A E, where capital W is the total weight of the bar. Okay. So, this is the way we can go for what? We can go for finding out the elongation of bar in different condition by applying the Hooke's law for finding out the elongations. Okay. We have gone through 3 cases. One, the elongation of prismatic bar. So, that the relation is P L upon A. Then for the elongation of tapered bar, that is 4 P L upon pi E d1 d2. Then the elongation of bar due to its own weight. So, we are getting 2 relation. One more thing which we can do with this, bar of varying cross section, So, now I have selected a bar of varying cross section. It has subjected to loads P1, P2, P3 and P4. The lengths are L1, L2, L3. Cross sections are A1, A2 and A3. These are the cross sections. So, how to find out? So, obviously, the delta L, the total elongation in the bar by the principle of superposition, delta L1 plus delta L2 plus delta L3. How to find out delta L1? So, just consider the first cross section, first length. Okay. So, it is delta L1. What is the load here? It is P1 L1 upon A1 E. Now, how to find out delta L2? Now, come to this surface. At this surface, at this plane, the load is P1 minus P2. I am considering this P1 also, and P2 is already here. So, P1 minus P2 P1 minus P2 into L2 divided by A2E. For finding out delta L3, I have two choices. Either I can write the equation as a P1 minus P2 plus P3, or I can take P4. So, P4 into L3 upon A3E. Another important condition here, that P1 minus P2 plus P3 minus P4 must be equal to 0. So, this is how we can go for the different type of problem. The bar of bearing cross section, here the cross section is changing, length is also changing, the loads are also different. So, for finding out the change in length of this type of problem, we can go with this kind of solution. For writing these P1 L1 upon A1E or P1 minus P2 L2 upon A2E, we can also draw the free body diagram also. So, just take the example of this two. Okay. So, I am coming one by one. First, I am drawing the free body diagram for length L2. Here the load is P1. So, obviously, for the elongation of this, the load must be P1 here. So, this P1 is pushing this surface. So, at L2 length, obviously, there must be P1 must be equal and opposite. Already here exists P2, here exists P2. So, the net force on this plane is P1 minus P2. So, obviously, on the other side it must be P1 minus P2. Directly I wrote there. Okay. I have shifted this force P1 here, or we can check from the free body diagram also. So, this is the way we can solve simple problems related to Hooke's law for finding out change in length. I hope by this video you will be able to understand how to go for simple numerical problems related to Hooke's law and change in length. Thank you for watching the video. Thank you very much. Thank you.